says let dy dx equals to f of x and y, and the initial value y at x sub 0 be equals to y sub 0 be an initial value problem. And suppose f and the partial derivative of f with respect to y are both continuous on a rectangle like R, which is defined as the set of all x and y's such that x is bounded between two constants a and b, and y is bounded between two constants c and d, and this rectangle includes the point x sub 0, y sub 0, such that R contains x sub 0, y sub 0. Well, this theorem says if these conditions are met, then for sure you have a unique solution for this initial value problem. Then there is a unique solution like phi and x in an interval x bounded between x sub 0 minus delta and x sub 0 plus delta, where delta is a small positive number. So this theorem guarantees that we're going to end up with a unique solution for this initial value problem. Very well. Now I expect you to ask, let's go back to the solution of an ODE. We talked about explicit solution, implicit solution. Now I expect you to ask, what if I want to analyze the nature of the solution? Or what if we encounter the case that we cannot find an explicit solution or implicit solution for a differential equation? What we can do? Well, here you can use technology, or you can use paper and pencil, graph the slope field, or use Isaac lines. So in this case, we would like to visualize the solutions. So to visualize the solution, we can use slope fields, or we can use Isaac lines. And finally, the easiest way, the fast way, is to use the technology. So a slope field and direction field are the same that we discussed in calculus. Let us go over a couple of examples to feel comfortable about using slope field, Isaac lines, and the technology. In this example, question says, well, you have the equation, the derivative of x with the derivative of y with respect to x is equal to x squared minus y. We would like to visualize the solution for this differential equation. Let us use slope field to visualize the solution or analyze the nature of the solution for this differential equation. So what are we going to do? As you remember, we're going to use a table. In that table, we're going to enter some values for x, some values for y, and also dy over dx. So x, y, dy over dx. Then we're going to use those little arrows representing the rate of change. If x is equal to 0, y equal to 0, you get 0 minus 0. So the rate of change is 0. It means that you have a flat line. X, y. At the origin, 0 and 0, we have a very small arrow, which is horizontal. Let's plug in another point. Suppose you have 1 and 0. Well, if I plug in 1 and 0, x squared minus y is just 1. So it means that the rate of change or the slope is equal to 1. At 1 and 0, point 1 and 0, the slope is 1. Well, what if I plug in, for example, 0 and 1? What do I get? I get 0 minus 1, which is negative 1. The slope is negative 1. So at 0 and 1, slope is negative 1. If we continue this process, we can plug in many values if we have time for x, for y. Continue. Plug in more points if you have time. Otherwise, we're going to use technology to visualize the slope field. One of the websites that you can use to visualize the solution of differential equation is this website. It's free. You just need to enter x squared minus y on the right-hand side of dy over dx and hit enter. And as you can see, the direction field with some solutions, the nature of the solutions are visible for us. Later on in this class, we're going to learn different techniques to actually solve this differential equation. And later on, you see that the solution, the family of solutions are following these curves.